Okay, welcome back. So in the previous video, we've just had a look at compressed path databases, CPDs. The key idea here, right, is we're in the field of search. We're trying to improve our search algorithms. We're trying to improve our search performance. Well, to do so, we are currently focusing on the avenue of improving our heuristics, right? So the better our estimates of the actual distance to go, well, the fewer node expansions we need to do and the faster our algorithms can terminate. So compressed path databases was the base idea that, well, obviously heuristic accuracy is important. Can we just do search beforehand? We have plenty of time, right, to compute and to store this massive database, right, of the actual distances from every possible location to every other. That is this all pairs table. So, well, that's all great and really pushes forward state of the art in types of environments where we actually have the time to be able to do that and the resources to actually store the CPD. Well, that does not often work in a lot of real-time problems, particularly when we're trying to do some form of online search. But very often, right, we don't actually have the time to sit around and wait that 20 hours to compute this massive distance table. So instead, we're going to turn to what is called differential heuristics. So this is another really cutting edge heuristic that is extremely performative. But we're kind of taking these core concepts, right? This idea, well, the idea that ideal heuristics are oracles, right? So like great heuristics, right, are ones that are oracles. They're perfect distances. They see the whole path. They tell me the actual cost that I need to search. Of course, this is our baseline idea, but as we've seen in CPDs, well, the issue is that this is extremely expensive to both compute and store. Okay? So, obviously we're going to have to do something differently here. Well, differential heuristics is really just as simple as the idea that, okay, we know we can't store all of it, but what happens if I do a subset, right? What happens if I choose, let's consider doing one first, okay? So I'm going to choose some location that I'm going to store all distances to, right? So instead of doing this all pair table, well, I'm going to choose one pivot P somewhere in the graph, okay? And I am going to, from this pivot P, compute the distances to every single other node. Again, this is just going to be one Dijkstra's call, right? You run an unbounded Dijkstra's, it finds the actual perfect distance to every other node in your entire graph. Similar to CPDs, if you haven't watched that video, note, right, that the table I'm drawing up here, this is going to, in the x-axis, we're looking at all possible goal states you could start from. And in the y-axis, we're doing all possible start states. What's important there is that I think this is often quite confusing the first time students look at this. What I'm considering is, say we have a regular 3x3 grid, right? There are only 9 states in that grid. Here, this table is not representing the actual grid itself. I'm trying to look at the all pairs table. So in a single axis, it is the length of n number of states. Here, in the 3x3 example, that means it would be 9 by 9, okay? So that's what we're looking at here. Well, I've defined a pivot to be essentially at the current 4th location. The same pivot, of course, the same state could be a goal node or a start node. But I'm computing the distance to everywhere else from this pivot. What this looks like in our little table here then is I would essentially color in the corresponding rows and columns as data that we now have. Okay, so I've drawn up the corresponding row and column from our pivot P. So instead of storing the all pairs, I have just done it for one node, from one node to everywhere else. Well, how is this even going to help us, right? What are the odds that when I'm given a problem, a start and target, that they relate to the pivot in any way? So what we're going to talk about then is that differential heuristics, the key idea here that's driving this forward and allowing us to essentially gain information from this heuristic. Well, what we're going to do is exploit our old friend, the triangle inequality. So I'm going to write that up here, and then we're going to walk through and draw an example of how this comes about and how the actual pivot and the distances it provides is actually going to be really, really informative and actually extremely useful to us during search. So first things first, we are going to be exploiting the triangle inequality. Okay, so how does the triangle inequality come about here? Right, so we have some form of start location, of course. We also have our target T. I constantly change between capital G for goal, capital T for target, small lowercase t for target. You're going to have to get used to that. And then now we have this third quantity, some pivot P. This has come out of nowhere. Well, essentially what happens, right, is in the real problem, we have the knowledge that who knows what path we take, right? It can be very roundabout. We can go multiple different ways. The exact relationship between our start and our pivot, and again, similarly, our pivot to our target, well, this is very unknown and actually arbitrary, but we're going to find out that we'll talk about the properties and where we want to select pivots to actually provide us with different and more useful or more informative information. But for now, right, it actually doesn't matter. We're saying this is a generic location. We chose the pivot randomly in our grid, in our graph, in our problem. Okay, how is this useful? Well, the last thing I'll draw is, of course, very similarly, there was some version of a path, that is what we're trying to look for, I guess, that's leading from the start to the target. If I start drawing up the distances here, right, so the distance from start to P, okay, I'm going to label that here, distance from S to the pivot P, then I'm going to look at what would be essentially the distance from the target to the pivot, so D from T to P, okay. And finally, we have, of course, the actual distance we're looking for is the distance from S to T. Okay, well, we have a triangle here. What is essentially the classic example here is based on the triangle inequality. Well, we've previously seen the triangle inequality come into play in terms of the consistency of heuristics, right? We're abusing this. The sum of two sides of the triangle have to be less than or equal to the third side, so A plus B is less than or equal to C. Well, there's this other very similarly related version of the triangle inequality, the inverse triangle inequality, which we can write up as follows. It is essentially saying the difference between the two sides, the difference of the absolute value between the two sides. So this is the distance from S to P minus the distance from T to P. Well, this is less than or equal to, this must be less than or equal to the distance from the start to the target. Okay, so we're abusing a mathematical concept from the triangle inequality, but what we're actually arriving at then is we're saying we have some function here in terms of the distance from the start and the target to some pivot, any generic pivot P. Well, we're saying that this must be less than or equal to the actual distance from the start to target. Okay, what this is starting to say then, this idea here, which is a pretty simple idea, this is going to be both a consistent and an admissible heuristic. This equation here, this left-hand side, is an underestimate, right, of the true distance between the start and the target. So that's quite exciting. This is why differential heuristics come into play, and this is why it works. So based on just selecting one pivot P, all of a sudden we could essentially store its distance to every other node in the graph, right? And during search, we can use this equation to essentially say, hey, from any location, well, I have this admissible and consistent estimate of where I want to go. So let's then talk about why is this actually powerful. Okay, so let's hone in on then, why are differential heuristics so useful and so powerful? Well, what might not be apparent here, so we kind of had this is also a property that does exist in CPDs, but in CPDs, right, we're really doing all of the work. We're storing the whole paths, or sorry, the first moves in this database, so it really kind of removes the need for online search in the first place, right? You just kind of replace the problem with this retrieval problem instead. differential heuristics, right, we're still performing search. We're still using our common A-star behaviors. It's just that we have this heuristic estimate that we're going to be getting from this triangle inequality that we haven't yet really discussed how we're going to be choosing pivots and some other details that I want to leave out for just now. But what's really important, why is this concept going to be so powerful? Well, what is not apparent, I think, in this situation is the idea that these are storing the actual distances, right? These are the actual distances in the real problem, including all of the obstacles and walls and detours and rooms and information about the actual problem, right? In all of the other simple heuristics we've been looking at within something like a grid map domain, well, the Manhattan distance, right, completely ignored walls. It was just the optimistic, I just walk directly there. Very similar to, again, the equivalent for the octile distance, which has diagonals, and then things like straight line distance. These baseline heuristics are useful, right, because they can inform our algorithms, and it means that we're actually able to have a complete and optimal search. But they were always missing key knowledge about the environment, the actual topology, what the problem looks like. What's really exciting is differential heuristics have that built in, right? If one side, if from the start to the pivot included a large detour, right, there was a massive wall in the way in our grid, well, the differential heuristic actually captured that information. It's letting you know that once I get around this wall, then the distance looks a lot shorter, right? It must be more similar to just a straight shot there. So that's exciting. Differential heuristics, I think what is often missed when you learn this concept in a computer science course is we say, hey, it's really useful, you see it in practical performance, but I think that key idea is missing. This is the first heuristic in regular heuristics that we're using in inline search that is informed about actually what the problem itself looks like, more or less. That relates then to the idea of selecting pivots, okay? Because where we select P is important. What we're trying to do is retrieve information about aspects of the map, about different locations in the map. So that's really exciting. The very first thing I want to note is, well, we are not going to often select just one pivot, right? We're saying, I don't have time to compute the whole table, but these problems are often usually substantially large, right? We're often working with grid maps that have dimensions that are hundreds by hundreds. Well, of course, then storing the whole distance table is going to be a massive endeavor. Instead, when we're looking at differential heuristics, well, we're going to compute a few pivots, a handful of pivots, and we'll see that only doing this amount of information is actually extremely useful for search still. So we often, I think, it's really dependent on the type of problem you're solving in the map. But as a little bit of an upfront, I think what often happens is we select around, say 10 to 15 pivots. The more pivots you do, obviously you're trading this pre-compute and it kind of takes away from your actual search time performance. Again, so we're using differential heuristics as kind of like this middle ground between the two. So you're saying, hey, if I'm going to be solving a bunch of railroad problems, right? Like I'm tasked with doing this pretty soon. I have 2 hours to compute a bunch of paths for all of these trains. Well, then maybe it is worthwhile, right? Because you're going to have hundreds of calls. You're trying to iteratively improve the solution, things like this. It's this multi-agent problem, which we haven't even discussed much yet. Well, in these kind of situations, doing the upfront work to take 10 to 15 minutes, well, if we can do that small amount of 10, 15-minute computation to essentially store this information, and it proves extremely useful and means we can conduct substantially more searches in the same amount of time, well, then that obviously, it proves itself, it becomes immediately worthwhile doing. That is where differential heuristics come in. And in those kind of situations, well, we're going to try to pick a handful of pivots, and we're going to try to strategically place them in the map to maximize the information we gain. So let's talk about that. How are we going to select pivots? Well, the first thing I want to note in terms of selecting pivots is the actual information we're retrieving from this distance. Well, the type of triangle actually matters. So the side lengths in respect to each other are important. So let's consider a few different triangles, right? So there are some that are kind of standard, right? Then there are these triangles with what essentially becomes an obtuse angle, right? And then there's other similar ones, right? Like these equilateral triangles where, well, or it can be tall, as we'll see. So there's a whole bunch of different triangles. Wow, how surprising. But this actually does have a large impact on the actual amount of information we can retrieve from the actual triangles. So to label them right, it was ST, ST, ST. And then there was always some pivot location, right? And where the pivot location is, we're abstractly representing as what kind of the resulting triangle looks like. Again, this is like a bit of an abstract concept because it actually relates to the actual distances within the maze, which might have a whole convoluted series of walkabouts and detours. Okay, so what I'm trying to get at though is that not all pivots are the same from the get-go. On top of that, there's also this idea that I'm telling you that differential pivots are really good, okay? Are they dominant? Do they always beat the Manhattan distance, these basic heuristics? The answer to that is absolutely no, okay? So I want to walk through examples here of where we could try to pick a pivot that's really dumb, okay? And then I think that will tie back immediately into this conversation we've been having. Okay, sorry, I've just modified the example very slightly. So in this problem in class, what I often do is I try to prompt the students to take 5 minutes to essentially select some pivot locations in the graph and kind of compute, just do the distance, right? To see essentially what kind of estimates start becoming returned. So of course, right, when we want our heuristic estimates to be informative, we want them to be as high as possible, as close to the real distance, the true distance, as we can get. We're already confirming that it is an admissible and consistent heuristic, so we don't have to worry about the idea of overestimating. What ends up happening then is we can select a few. At some point in time, a student will put the pivot, nice and simply, directly between the start and the target. Okay, so in this case, I just want to draw up what this distance would look like then. So the distance from the start to the pivot is, in this case, 3, okay? So we have 3 minus, well, the distance from the target to the pivot is 3, okay? And this is less than or equal to the true distance between the start and the target, which is 6. Essentially though, this is our heuristic estimate. Well, we just got the heuristic value of 0. That is completely uninformative, right? That is a terrible heuristic. It provided us no additional information. Obviously, it's a little simple, right? This is, of course, it's directly in the straight line. It doesn't matter. You would just walk in the straight line. Okay. However, this, if you actually convince yourself, this follows everywhere in the entire graph, no matter how far away it was. If we're in this halfway point between the two heuristics, well, if it has the same distance, it's uninformed. So this becomes a little bit awkward, right? Once we start putting in walls and things like that, this still holds. This might wiggle, right? So hey, if you had to do a bit of a detour here, well, there's a new location that is completely uninformative because it thinks the triangle is essentially like this balanced version, right? When these two upper sides are the same, we actually are provided with no additional information in the problem. So that's quite silly. Okay, so when we return back to these kind of triangles, what we're actually looking for, I'm saying that these two situations here are really bad, okay? Our heuristic estimates are 0 or near 0, right? They're giving us very diminishing value, diminishing returns. Instead, these upper triangles are better. This one's good. It has a difference, right? So what we're looking for is a difference in the side lengths from the start to the pivot and the target to the pivot. This example is the excellent one. What we're really looking for is a pivot that is really far away from one of our locations, but close to the other. Mathematically, this means, right, in your actual absolute value of the difference between these two values, right, we wanted our heuristic estimate to give us the most informative, the highest value possible. Well, that corresponds to the situations, to the types of triangles, right, where one of the sides was really long and one was short. In these situations, we obtain the greatest difference, we obtain the greatest information. So that is quite exciting. What that means then is we start to look for pivot locations where we can, if we drew the triangle, obtain these kind of similar shapes. It's a little bit hard because, of course, in a real grid map, again, you don't know where your start and target locations will be more often than not. Again, everything really depends on the problem you're solving, but we usually don't. In these situations, what ends up happening then, we're going to write down a list of how can we try to select good pivots. So let's do that here. Okay, so let's talk about some good choices we can make when trying to choose pivots. Oftentimes, essentially, we want our pivots to be in areas that have low reach, right? They're not commonly in between, right? Related to areas that are along common shortest paths. Okay, when they kind of overlap with the actual area we're going to be searching in, we're seeing that they provide less information. So what that's lending us towards is that we like to initialize pivots and essentially in the corners of maps is what I'm trying to get at. We want them to be far away from a lot of the start and targets, which means that the triangle is more likely to be one that benefits us. Another way to write that, as I kind of said as part of that description, is they are not commonly along shortest paths. So another way to say that, which I've kind of said in that description, is that the pivots are not along common shortest paths. So do not appear in common shortest paths. Okay? So imagine you've done a bunch of pre-computation. We see this heat map of where a lot of the searches are going to happen, or we could hopefully maybe just assume that it's going to be kind of in a bubble moving towards the centers of the map. Well, then we can try to choose pivots that are far away. On top of that though, we're talking about the idea that we're going to be selecting multiple pivots. So in the world that I just drew this bottom pivot down here, well, where might we want the next pivot? I think a common way to do it is to say, okay, well, we still like this corner idea. Maybe I'll choose the other corner. That seems quite intuitive. Maybe the next one, okay, maybe you could select another corner. Okay, is this now going to be more useful? I think it starts to become a little bit maybe less convincing about that aspect of where we're going to pick it next. Well, what you might start seeing, and the way we do this often, is we start essentially selecting pivots that are maximally far away from each other. So you kind of want to spread the pivots out. What this is actually meaning and doing in the world is that essentially when we define a pivot, right, we're kind of like gaining information about a specific area, and they gain the most information in it, like closer to themselves, right? This is like filling in, hey, there's a bunch of walls over here. Oh, this was something that's important. We could draw, when we put in a pivot, right, there's kind of like this heat map around it. And so we're trying to, in order to maximize our information, well, we want to be informed about different parts of the world. As we grow this amount of information, we're most likely to at least have one of these pivots provide something useful to us in order to speed up search. So that's kind of a neat idea. We just have this idea that they essentially want to be far away from each other. Okay, finally then, this isn't really what they are, but we're kind of talking about the idea. We want to select a series of pivots, right? But there's a trade-off, right? You start doing more pre-compute, which means you're wasting time. Maybe you're not improving search beyond a certain amount. So oftentimes we get around 10 to 15 pivots, and then our performance starts to diminish thereafter. So, there's going to be some form of sweet spot in the actual map and problems you're solving, and you might have to kind of figure that out based on some trial and error and practical performance. The very last thing I want to note about pivots and differential heuristics is, of course, very similar to the other conversations I've had about heuristics. Well, we know that all of the estimates from all of the pivots are admissible and consistent based on our definition. Well, it just means that we can always you can max over the information provided by each pivot. Okay, so our heuristic value for these 10 pivots we've chosen, well, we can choose the best one every time, the most informative. That's where we're getting these the additional benefit from trying to define different pivots in different parts of the map. But I think pivots are extremely exciting. Differential heuristics is a really, really cool idea to start seeing all of this come to life. And yeah, they're extremely performative and really push forward a lot of state of the art. So when you go to solve your own problems, maybe consider, right, spending a little bit of effort, just run a Dijkstra search, start caching some results, and all of a sudden this can start improving your performance. With all of that said, please join me in the next video where I talk about a really, really interesting and very different but advanced heuristic that is used in several parts of the literature, but I think it's not used too much yet because I think it's a difficult concept to understand because it's so different from these very visual and intuitive, simple equations that we can define. I'm going to be talking about the fast map heuristic, which is going to be using essentially mappings. So mathematical mappings from your problem to this abstract n-dimensional vector space where we can end up with approximations of the real distances and map that back to the original problem. So fast maps are super exciting. I think they're really cool in the literature. I discovered this not through my university master's level subject, but through my own PhD and writing up my thesis. So please join me there when we discuss that. Thanks.